Thank you. So this is a topic that many of you are familiar with, some of you have worked on. I'm starting with a quote from our host from 2000 that turns out, apart from the estimate of when advanced LIGO will be ready, to be pretty accurate. So this early work is based on toy models with ellipsoids and here with quasi-equilibrium models, and then work using general relativistic simulations done in '09 with simulations by Shibata based on initial data by Uryu and Markakis, and these other people, Jocelyn Reed and Jolene Creighton, doing the data analysis. And a much larger set of models with a larger set of equations of state looked at subsequently here and by a set of other people. So these are my collaborators and a number of other people doing similar work and trying to estimate the accuracy with which you can extract information about the neutron-star equation of state here from double neutron-star inspiral and from neutron-star black hole inspiral. There was a parallel analytic study of early inspiral in a post-Newtonian framework by a number of people. Well, that includes de Moore, Nagar, and Velen up here, I guess, although they extend to late inspiral using their effective one-body approximation. And then more recently with black hole neutron-star codes coming into existence, a study of the analogous question for black holes and neutron stars. So we're looking at the equation of state of a neutron star, and the question in the core really is how are the quarks grouped, and do you have strange quarks or just up and down quarks? So you have only nucleons. Is the Fermi level of the neutron Fermi level at the center where the density is highest large enough that it's energetically favorable to turn neutrons into hyperons, favorable to turn down quarks into strange quarks, and so that gives you this possibility of having hyperons in the core, or a possibility of having a core that consists of strange matter, and an unlikely but not completely ruled out possibility that what we call neutron stars are really strange stars, large collections of up, down, and strange quarks in a single bag the size of the star itself. Because of this possibility of a wide variety of different ways of grouping the quarks and different parameters that come into the Lagrangians that are associated with those different groupings, the number of parameters for a fundamental, roughly fundamental Lagrangian is quite large, and much larger than the number of observational constraints that we have at present, or that we'll have in a few years, that can be used to constrain the equation of state. So to deal with that, it's helpful to have a phenomenological equation of state with a number of parameters that is large enough to model the universe of candidate equations of state, but small enough to be constrained by the observations. So no small fundamental set of parameters, and instead we use a piecewise polytrope noting that both non-relativistic and highly relativistic ideal gases have equations of state that look like PV to the gamma equals constant, or pressure equals a constant times rho, which I'm using for baryon density rather than energy density. P equals K rho to the gamma. So this is a set of a group of candidate equations of state, so a representative collection. And one can model these by a piecewise polytrope where the slope of log p versus log rho is constant in these pieces, and then we have an overall height to this curve, translating it up to match one of these things, one of these candidate equations of state. So we specify gamma at 3 different densities, translate the P or rho curve up and down, and the motivation for doing it in this way is that the pressure at roughly twice nuclear density is closely correlated with the radius of the neutron star. So this was noticed by Latimer and Prakash, and we use the pressure as one of these parameters. You could use the pressure and 3 gammas, which is the way I'm going to present this, or you can use the pressures at 3 different densities for an equivalent representation, which was used later by Ferrier, Olzo, Gordon, Bain, and Goover. The universe of candidates has a couple of roughly preferred dividing densities that you can pick, and then with those fixed, you have four parameters to specify the equation of state, and that gives a pretty decent parameterization to within a few percent for a given equation of state. Lee took a different parameterization using a spectral representation here, a power law for the exponent in this way of representing gamma. And if you want to go from a set of observations and go back and extract an equation of state, this is likely to be the current best way to do it. So in terms of these parameters, we can look at the constraints that are set by observations. So there are, and by theory. So there are hard theoretical constraints. The equation of state is essentially known below nuclear density, and we have a constraint set by causality that signals can't propagate faster than speed of light. That for perfect fluid is saying that the speed of sound is less than the speed of light. And for a one-parameter equation of state, you have this relation dp d epsilon. For perfect fluid, dp d epsilon less than 1, where epsilon is the energy density. So that's one constraint, and then you have hard astrophysical constraints from the measurement of neutron star masses, a couple of accurately measured neutron star masses greater than 2 solar masses, and a largest measurement of neutron star spin at 716 hertz. Now this is pretty weak because for most equations of state, for almost all equations of state, the upper limit on neutron star spin is around twice this. Certainly, well, for almost all equations of state, it's higher than this. For typical equations of state, it's on the order of twice this. And so it's really the maximum mass that serves as the only model-independent observation that gives an effective constraint on the equation of state. So if we look at this parameterized equation of state with 3 parameters, this pressure at about twice nuclear density, the slope of logarithmic slope of the p rho curve at about twice that, 4 times or so nuclear density, and then at the highest densities, we have a constraint set by causality that says that the pressure itself can't be too high. You violate causality if pressure at nuclear density is too high, or if gamma 3, so you're looking at the inner core of the star, and you can't have gamma be too large at the inner core of the star. That slightly overstates what's happening, because if you take this polytropic equation of state, then it's valid only for, you're only getting information for neutron stars whose central density is below the central density of the maximum mass neutron star. So, so there's a region of configuration of the equation of state space up here, which just doesn't appear in neutron star models, so there's no constraint on it. But this is essentially the way to picture causality. And then the maximum mass of a neutron star imposes something like an opposite constraint. You have to be soft enough to satisfy causality. If you're too stiff, equation of state, it's not causal, and at the same time you have to be stiff enough in the inner core to allow a maximum mass of at least two solar masses. So that gives a combined region of the allowed space in here above this maximum mass constraint. This is so mass greater than about 2 solar masses, and restricted in this region by causality. Okay, next thing to say over here is that if you can simultaneously measure 2 properties of a single star accurately, then that restricts the equation of state to a single surface. So it's much stronger than measuring a single property for a single neutron star, a different property for another neutron star. So I emphasize this because this is what one expects to do with a gravitational wave observation. You should be able to get the masses of the neutron stars. So if we ignore error bars, you get the masses of the neutron stars, and then you get one additional parameter from the inspiral itself, and that then restricts you to a one-dimensional lower region in the equation of state space. There are already model-dependent measurements of neutron star radii. So a number of papers in recent years, starting with these papers by Ben Paradis, Lewin, and Tom, and then on thermonuclear bursts. So you have a helium flash, sudden fusion, hydrogen to helium at the surface of the neutron star. The atmosphere expands, then it contracts, and if you watch the emission from this burst, at the end of the burst, the atmosphere should settle down to the radius of the neutron star. It's hot enough to see. The burst has covered the entire star, and so you expect roughly isotropic emission from the surface of the neutron star. At the end of the burst, you're back down to the radius of the neutron star, and you can then deduce the radius from temperature and distance to the neutron star. And then another set of neutron stars, accreting neutron stars, in their quiescent stage, again, where one is looking at quiescence when you're not accreting and heating up a particular part of the star. So again, you're hoping to look at isotropic radiation from the surface of the star. Now, the constraints that you infer from this, people get fairly sharply limited claims for the radius that they infer from these observations of the bursts and the quiescent X-ray sources. But the differences between different groups is significantly larger than the systematic errors that are assigned by each group. So these are still, there's still a substantial worry on the model dependence of these observations. So here's work by Ferrioso, Gordon Bine, Goover in 2010, and you can see that these 2 sigma error bars are restricting the, well, let's see, what I wanted to show was the error bars over here in the radius. So they're restricting the radius over here, not too sharply, but notice that the radius is, the radii are claimed to be somewhere between 8 and 10 kilometers. So pretty small, sort of surprisingly small radius, given the need for an equation of state stiff enough to have a 2 solar mass neutron star. And so that's, so another analysis by Guyot et al., 2013, determines the radius between between 10, so 9.1 plus or minus 1.5 or so kilometers. All right, so again, a pretty small radius, and then Latimer and Steiner look at the same data, get roughly the same estimate of radius if they use only that data, and then if they use that data plus the requirement that you have causality and the existence of a 2 solar mass neutron star, then they move the radius up between 10.9 and 12.7 kilometers. Okay, so maybe this is the right range of radius, but it gives you, again, gives you some worry if what you're getting without putting in the extra information is something on the order of 9 kilometers. So I want to emphasize that because the accuracy over here is at least as good as what we could expect to get from observations of binary inspiral from gravitational waves. But the real advantage of looking at gravitational waves is the model independence. So you have a real sanity check on these optical observations, well, these electromagnetic observations.
So how does the causality assumption affect their estimate of the measures?
Well, so it's just gonna rule out. So the models that these people, so if you want to get a radius that's this small and still get yourself a 2 solar mass neutron star. So I think Guyot was trying to do that, not imposing causality, but trying to get 2 solar masses. And I mean, that's not what they used in this estimate. But then they looked and tried to see what equations of state could fit this and still be consistent. So they found a set of equations of state, but you have to be very stiff at the center and then soft so that it compresses down on the center. And most of these equations of state they looked at were so stiff at the center they violated causality. So that's okay. Okay, so future constraints. Well, of course, this is what we're looking at. I won't talk about constraints from the mode frequencies for merged stars, but for hypermassive neutron stars, you may have long-lived oscillations, so could have 100 cycles with a decreasing amplitude, might be able to see the first 10 or 20. You have to, that is model dependent. You have to figure out what the differential rotation is, or at least find out how sensitive the mode frequencies are to the possible inaccuracy in modeling differential rotation and modeling the temperature of the neutron star afterwards. And then if you want to get information about the cold equation of state, you're going to have to extrapolate down from the hot equation of state after merge to the cold equation of state prior to merge. Okay, and then increasing accuracy expected from future missions for electromagnetic observations. Well, signal from a binary neutron star. I don't think in this audience I need to talk about that. And the departure of the signal in the late inspiral, still accessible to broadband LIGO, broadband advanced LIGO. Without broadband, hard to see it. And this is the noise curve for probably ETD, the Einstein telescope. All right, well, departure from point particle inspiral at lower frequency for neutron stars with larger radius because the tidal force is greater. So this an illustration from Ben Lackey to emphasize the coalescence earlier for a stiffer equation of state with a larger radius. During the course of the inspiral, if you have a larger radius, the tidal forces are larger, and that means that you're deforming the stars more, and so more of the energy of the inspiral is going into the work done to deform the stars. That means you're losing energy more rapidly as the inspiral proceeds, and as you get to the later stages of inspiral, the rate at which you pump energy into the deformation is increasing. So the inspiral, you lose energy more quickly, you progress more rapidly through the cycle of frequencies, and you merge more quickly at a lower frequency. The tidal forces are governed by the deformability of the neutron star. So at large separation, you can define a deformability by imposing a quadrupole field on the neutron star. So that means a field that asymptotically looks like quadrupole times r squared, and then you look at the induced asymptotic 1 over r cubed quadrupole contribution from the neutron star. For this group, I think it's worth going through that in a little detail in a minute. So the deformability is roughly proportional to radius of the neutron star to the 5th power times the quadrupole Love number. So measuring, well, you have r to the 5th, and K2 also has the property that at greater compactness, when r is smaller, K2 is smaller, and so this is slightly greater than an r to the 5th dependence. So measuring lambda is roughly equivalent to measuring r, and in fact, I noticed in a recent paper by Demour et al., they emphasize this fact by writing r tidal as 2/3 K2. Well, so you can, so I think they give a useful mnemonic saying that what you're measuring is what they call a tidal radius, just taking the 5th power of this and writing 2/3 K2 to the 1/5 times r as the effective radius that you're measuring in looking at the early inspiral. So this near equivalence, so I'd say equivalence up to ability of advanced LIGO to measure this, of lambda and the radius is emphasized by this plot. So you're looking at a polytrope over here, So a set of polynotropes with different values of gamma, log P1. We're looking at the curves in this parameter space, different gammas, different P's at twice nuclear density. And the curves in this equation of state space of constant radius nearly align then with the curves of constant deformability. Okay, so just showing you the what to expect for difference in waveforms. So here's a stiff equation of state looking at plus and cross polarizations for the stiff equation of state prior to merger and then merger. And here for a soft equation of state where you continue on for several more cycles before merger. So you sweep through the frequencies more quickly, you merge more quickly. Here you have a phase difference and then a continued signal for several cycles after the merger of the larger star. So that difference, both the difference in phase and the difference in the length of the wave train, gives you an effective measurement of log of P, or effective measurement of P at twice nuclear density. So that's the guy that's correlated to the radius. And you can measure that. So here with broadband, or if narrow banding is ever used, an accurate logarithmic accuracy of about 0.1 or 0.2, depending on how small the radius of the neutron star is. So the smaller the radius of the neutron star, the less accurate you are. So easy to distinguish 12 from 14 kilometers, difficult to distinguish 8 from 10 kilometers. And here's the accuracy, again, the accuracy with which you can get the radius broadband, so plus or minus something over half a kilometer. If well, let's see, radius of 10 kilometers, radius of 13 kilometers, this gives an error of 1.7. So I want to say one other thing before turning to black hole neutron star inspiral, and that, so the numbers I was showing you were from the earliest numerical analysis of this. The later numerical analysis included a larger family of equations of state. So the question is, can you measure other parameters in the equation of state? And the answer is essentially no. You get one parameter out of the equation of, you get one parameter for the neutron star, and that's the deformability, despite the fact that that deformability accurately tells you the deformation of the neutron star only for early inspiral, for large separation. So when the separation is small, you get a number of different multipoles. The actual deformation is much larger than 3 times larger or more than the post-Newtonian deformation that you would predict from the post-Newtonian formula you're using to define lambda. And nevertheless, all you get is lambda out of this information. That's the first thing. Then the accuracy that I was quoting you is reduced by so the early paper didn't look at correlations between lambda and other parameters that you're measuring in the inspiral, the masses of the neutron stars. So there's some correlation, and if you include the correlation, the error is worse by possibly a factor of 2. On the other hand, the estimates only looked at late inspiral, and if you include both, if you match the early post-Newtonian inspiral waveform, if you have an accurate match between early post-Newtonian inspiral waveform and the late waveform, then the increase in accuracy from including the total waveform is essentially the same as the decrease from neglecting these correlations. So those estimates are still decent for the expected accuracy that you can measure the radius of the neutron star. All right, so departure from, so let's look now at black hole neutron star inspiral. Well, for a black hole, there's a common statement from Eric Poisson that the deformability of a black hole is 0. So if you impose a quadrupole field at infinity that goes like r squared times quadrupole at infinity, and then you look to see what the induced quadrupole moment of the black hole is, you get 0 if you use the circumferential radius to define the 1 over r cubed part of the metric. All right, this is a little peculiar, though. The problem is that you're imposing a field that grows like r squared at infinity. You have to define what you mean by a radial coordinate so that you know what the 1 over r cubed part is. So if you change that radial coordinate by something that goes like 1 over r to the 5th, you change its definition by an angle-dependent something that goes like 1 over r to the 5th, then you change this definition of lambda. So using that for a Newtonian star, this is all well defined. For a relativistic star, it's less well defined. And saying that it's 0 for a black hole is gauge dependent in this sense. It depends on your definition of the radial coordinate. Having said that, it's still the case that black holes represent the models with the smallest deformation that we have available. So there is energy loss in the black hole, and it's really the measure of energy loss that, well, that's one way you could define a meaning of tidal deformation. But if you're going to compare neutron star waveforms to point particle inspiral, you don't have point particles in general relativity, and black holes serve as, so black hole, spinless black hole inspiral serves as the point particle model to compare it. So for this analysis, for black hole neutron star inspiral, and for the last of our neutron star studies, we used a grid in this parameter space. So we have, again, the pressure at twice nuclear density, the slope of the curve above that, and then a set of essentially evenly spaced points in the parameter space to look at the effect on inspiral. So we have a set of simulations that give waveforms for different mass ratios. So here's waveforms for non-rotating black holes with mass ratios 2 and 5. Well, for smaller mass ratios, as you know, you're going to have larger tidal effects on the neutron star. Black hole mass is smaller, neutron star gets closer before coalescence, and you get larger tides, and so an earlier coalescence, larger tidal effect. Here's two equations of state with the same mass ratio. So a mass ratio of 3, an equation of state with 13.6 kilometers, and an equation of state for which the neutron star is 11 kilometers, 13.6 again, coalescing much earlier than the 11 kilometers. Well, for black hole neutron star, the tidal effects are typically smaller because the mass ratio is larger. And so the net change in phase is smaller by the time you get to coalescence, but there's a dramatic difference in the cutoff frequency that you see after coalescence, that marks the end of the coalescence of the inspiral. So you have earlier coalescence and less ring down for stiffer equations of state. Soft equation of state, small neutron star, plunges into the black hole, excites the black hole, and gives you a larger ring down. Okay, so for a comparison between black hole neutron star and neutron star inspiral, for black hole neutron star, long-term phase difference is important for both, but the cutoff frequency then is as important as the phase difference. Phase difference is smaller, cutoff frequency is dramatically different. You have smaller tides in the black hole neutron star case, fewer expected events for a given mass ratio, and that means you're less likely to gain equation of state information from black hole neutron stars, despite the lower frequency of the final orbit. And finally, this question of what neutron star property can be measured. So we're looking at this set of different parameters, and superimposed on these lines of constant lambda are the error ellipsoids for a measurement, in this case by ET, so that you get small ellipsoids and see how they line up. So what do you see? Well, this ellipsoid is narrow in this direction. So you get a good measurement of something perpendicular to the ellipse and almost no measurement. So this actual size of the ellipse is large and inaccurately determined by the analysis. What is determined well is this, and this is really all you can claim to measure, the direction perpendicular to the ellipse. And the ellipses, you can see, very nearly line up with, again, with the lines of constant radius or the lines of deformability lambda. So these are 1 sigma errors for Einstein telescope. So very good. So Einstein telescope can give you, and even smaller errors for neutron star. So you get very good measurements in principle for events at 100 megaparsecs for neutron star. There are any for neutron star black holes. This is for mass ratio of 2, spinless black hole, and again, amazingly close correlation between the ellipses and the lines of constant lambda. Finally, so this is saying changing the mass ratio. So this was the mass ratio over here of a larger mass ratio, and this is a mass ratio of 2. Again, you're lining up very closely, and here you're changing the spin to A over M equals 0.75, and nothing has changed in the direction of the ellipses. They're again lined up amazingly closely with the lines of constant lambda. Okay, so again, errors for ET telescope. For advanced LIGO, so you can compare the error over here, an order of magnitude difference in the error. So this is this error in this tidal radius. lambda to the 1/5. So the error in the tidal radius looks like 0.05 for a typical tidal radius of on the order of 4 kilometers. Well, this would be 4 times, this would be about 9 kilometers for the tidal radius. Uh, so very accurate measurement from ETD. So on the order of a percent. For advanced LIGO, much worse. As expected, errors larger than 10%. And then a quote from a number of you with a comparable statement on difficulty of measuring using black hole neutron stars to measure equation of state with advanced LIGO. So next generation, you should be in good shape. You should also by that time have more reliable electromagnetic observations and and here you need a number of events before you can get one close enough or aligned accurately enough to give you a measurement of the equation of state. So to summarize, I want to emphasize this fact that equations of state with the same lambda are degenerate. And that means that if you want to create a library of templates, all you have to do is make a simple library. You can just use a single polytrope matched, say, to a low density equation of state, and just have the single polytropic index vary over a plausible region of allowed radii, giving you a plausible region of allowed radii. And that will do it. You don't have to have a large library that spans the space of allowable equations of state. So I think that's a useful thing. And really the most important job now is to get a set of templates. So I would say a set of templates for a single polytropic equation of state that are reliable, have a Matter Ninja project, get a set of reliable templates, and then hope that you can get a long enough black hole simulation that you can match neutron-star templates at large distances to a black hole. Well, get a combined template from an accurate black hole inspiral matched to post-Newtonian so that you have a nice accurate post-Newtonian effective one body, whatever you want to call it, effective inspiral matched to your numerical templates for just a single parameter's worth of equations of state, and that should really be good enough to get your equation of state information out of advanced LIGO. Okay, well, I already talked about that. I think I'll stop with that sermon. Yeah, I think it's I'd say the main, so yeah, it's this piece over here. You're getting much better signal to noise up here and a significantly longer piece of the signal at the end. Yeah. I would say that for the inspiral, you didn't find a significant difference between broadband LIGO and narrow banding. But if you want to look at oscillations after the inspiral, then I think you could. So I haven't studied it. My presumption is you can get if you see a set of these to begin with, you could get good accuracy for the frequencies you want to pick up, which should be pretty close from one coalescence to another. So you ought to know what the frequencies are. You ought to be able to tune your narrowband detector to those frequencies. So I would say for getting the frequencies of oscillations out, if you are seeing them, if you don't have prompt collapse, and you are seeing 10, 20 cycles of oscillation after inspiral, that's the way to do it. Yeah. Uh-huh. Yeah. Yeah. So for neutron star, neutron star. Yeah. 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 So right. So so I have. So this was not from your work, but from work by Markakis and Ben Lackey. We're finding uncertainty decreasing in usual statistical way as square root of number of sources. Is that what you find? Do you do better than that? Yeah. Uh-huh. So constraining lambda itself or constraining the fifth root of lambda? Lambda itself to 10%. So, but if you constrain lambda, then you're constraining the radius to about a fifth of that. So you're saying with 10 measurements, I better read this, but okay. That's significantly, yeah. So I mean, it's smaller. So our estimate would be something like 5%, I guess, for 10 sources, and you're getting down to about 2%. Radius down to 2% with 10. Well, we'll find out. Uh, yeah. there are other